In the Sawtooth oscillator active circuit shown here, implemented using 3 op-amps and one junction field effect transistor N-channel type, in which source is left side here, gate, and then drain on the right side. Also one bipolar junction transistor BJT as shown here, base, collector, emitter, that combined with op-amp number 1 and a potentiometer of 1 mega ohm and a 4 volt fixed voltage, realizing a controllable current source here that adjusts the current of the collector of this BJT, that will help us with discharging, or charging this cap, and effectively helping us with generating this sawtooth waveform. We want to see how this is working and what are the components, what are the parameters that define the period of this sawtooth waveform, or effectively the frequency of that. We will see that the left side or the right side of this circuit, the combination of op-amp 3 and the series of this cap and potentiometer, controls effectively how high this sawtooth can rise. So that's the big picture. To quickly analyze the circuit, let's focus on the left side and basically BJT combined with op-amp 1 and potentiometer of 1 meg, and let's analyze that. To quickly do that, please notice that we have 10 and minus 10 volt supplies connected for op-amp 1, and also 10 and minus 10 supplies connected for op-amp 2. So effectively what happens is op-amps 1 and 2 are properly biased, and the other important thing is outputs of these op-amps connected to negative inverting terminal, so input terminal. So you can see that output is connected to negative. So for these two op-amps, I'm going to write here on top op-amps 1 and 2 properly biased with negative feedback, and as a result they are operating in linear region, and therefore that means virtual short is valid for these op-amps. So virtual short is valid, which means that the voltage at positive input terminal for these two op-amps is the same as voltage at negative terminal. And you can see that the positive terminal of these two op-amps connected to 0, so therefore we have 0 volt here, and as a result, because of virtual short, the negative terminal is also at 0 effectively, which we refer to as virtual ground. So we have 0 volt here and we have 0 volt here. What is the benefit of this observation? Look at the series of 10 kilo ohm fixed and 1 mega ohm potentiometer variable resistor. This series is on one side fed by 4 volt supply, on the other side fixed at 0 volt. Now because of that, we can compute the current that is going through the series of 1 mega and 10k. If we set this R variable resistor potentiometer, if we set it to, so I'm going to write it here, R min, or minimum value of this resistor, is of course 0, and R max is 1 mega ohm. So if I'm just trying to find the range of, basically the range of this current I, and that current, just to make sure we notice that, is the same as the current that is flowing through the base of transistor, because this whole current has to go this way. There is no way it can go through the input terminal of ideal op-amp, because input terminal of ideal op-amp has practically infinite impedance. What I can say is I base maximum happens when we are setting the R min. Basically R is 0. When R is 0, the series of this 10k and 1 meg is effectively just 10k. So in that case I can say IB max is equal to just 4 volt over 10k, which becomes 0.4 milliamp. So I'm going to write it here, 0.4 milliamp. Okay, the other thing is, let's make a practical assumption that the beta of this transistor, BJT, is a practical value like 100. A very reasonable practical value for beta of a BJT transistor. As a result, that means the collector current is 100 times the base current. So I collector max happens when I base max, beta times I base max. So is effectively is equal to 100 beta times the base current max 0.4 milliamp. So as a result, we get 40 milliamp maximum current for the collector of transistor BJT. As a result, you can also say I base minimum happens when the potentiometer resistor is at max value, which is 1 mega ohm. When that happens, of course, we get roughly, you can say that when that is the case, the series of 10K and 1 meg is practically 1 meg. So I'm going to write it here, roughly 4 volt divided by 1 mega ohm, which means 4 microamp. So that means I collector minimum for bipolar junction transistor is beta I base minimum for the bipolar junction or BJT, which is 100 times 4 microamp. So I get 0.4 milliamp. Okay, so we found the minimum and maximum current that we can control using the potentiometer that appears at the collector of the BJT transistor. What's the benefit of that? That IC can only go this way because it cannot go through the or come out of the input terminal of op-amp number 2. So there is nothing that that can go or come out of the input terminal. Now, at the beginning of operation, the cap has 0 charge. So that we know. I'm going to move this whole cap to here. The cap has 0 charge. Let me just make sure that I can, there you go. Okay. So the cap has the 0.2 nanofarad cap that we have, the main cap in the circuit has 0 charge. I can effectively show this way that the voltage across cap at the beginning of operation is 0, because on one side we have virtual ground, 0 volt. It's important to note that left side of cap is forced to 0, so is 0, and the same as voltage of the source of the junction field effect transistor or JFET, always 0. So the only thing that is changing is effectively the right side of the cap, that is when it's charging up, which is the same as output of the op-amp 2. So I'm going to refer to it as V2. The waveform you see here is for V2. When the cap is charging up, we are seeing that the waveform is rising. So if I show the time, at time 0 we are at 0 volt for V2, and as time is progressing, V2 is increasing. To what level? To what peak value? That is defined by this portion of the circuit, as I'm going to explain. Okay, at the beginning of operation we are at 0 for V2. So basically V2 is 0. This cap on this side is 0, and you can see that op-amp 3 is connected in a positive feedback mode. Output is connected to positive terminal, so it's effectively just a comparator. It has a positive feedback. So by comparator I mean op-amp 3 just monitors what's the 4 volt at negative terminal with whatever voltage at positive. The moment negative terminal has higher voltage, like the one that is, it would push the output to negative supply. So negative 10 volt is here. So I'm going to show, just as a reference, I'm going to show time, and at time t equal to 0, So maybe I show it here, because we have, so at time t equal to 0, I'm going to show V3, or the output of op-amp 3, which let's not forget is effectively VGS, because V3 is VG and VS is 0, so V3 is VGS. Okay, so I'm going to write it here. VGS is equal to V3 in the circuit. At the beginning of operation, at time 0, VGS equal to V3 is negative 10, as we just talked about. So it's negative 10. When that is the case, VGS of, when VGS, so I'm going to write it here. When VGS is negative 10 volt, it's too low. It will shut down. So I am going to shift this here. Okay, so when VGS is at negative 10, it will turn off. So I'm going to put it here. JFET turns off. It's too low. It will kill the JFET and effectively just turns off. When it turns off, you only have this cap that this current IC flows through and charges it up. So a constant current start charging up the cap, and therefore the voltage of, as a result, the voltage of the cap, which is V2, start rising up with a fixed slope. So hence the sawtooth. Alright, so what we have is this situation right now. Okay, so we have junction field effect transistor JFET off, and during this time, as I just mentioned, we have the V2, so this is the V3. Now we have V2 from 0 volt rising up. Okay, so rising up while still off. So it's still negative 10 volt for V3 or VGS. Okay, so during this time, how fast, or let's say what is the period of this sawtooth then? It can be computed this way. I'm going to write it here. So during this time, we are saying for the cap, I can say it's just dq is equal to c dv. The charge of cap is c times the delta, or change in the voltage of cap, is proportional to the delta in cap charge. So as a result, I can say I dt, which is basically the current of cap times change in time, is C delta in voltage, and then I can say integral I dt is integral C dv. There is an ultimate voltage for the cap, which is the point that this point gets to 4 volt. When this point gets to 4 volt, the comparator notices that the voltage at positive terminal starts becoming more than voltage at negative terminal, and hence it would switch the output from negative 10 to maximum allowed value, which is then forced to be 0 because of the diode at the output, and also maybe the limitation of the output stage of the comparator. So instead of negative 10, output jumps to 0 then. So I'm going to show it here. Output jumps to 0. Roughly. And now, because VGS becomes 0, so 0 means VGS is 0. So I'm going to write it here. And because VGS is 0, now it's VGS very reasonable high value actually. So JFET is not only on, is actually powerfully on with a minimal on resistor. So JFET on. I'm sort of exaggerating this duration of JFET on, but that's the best way I can do in terms of visualizing it. So what is that on time? Meaning that when we get to 4 volt here, then we have this change to 0, and as a result now we have this JFET turned on. So I'm going to show it here before continuing with the equation of the charging of the cap. So what I have is this situation. I have JFET on, which with a VGS of 0. So VGS 0. So this translates to, or is logically the same as, an on resistor. So R on, a very low on resistor, which for JFET with the VGS of 0, it's not strange to have R on the order of, say, 20 ohm or 25 ohm. And we have, of course, the main cap of the circuit in parallel. So the main cap of the circuit in parallel has plus minus 4 volt at the, let's say, during this process. So immediately we'll get discharged by a very small resistor. So basically the time constant of discharge is pretty small, that I can calculate that. So time constant is just R on times the main cap of the circuit times 0.2 nanofarad. So as a result it become, let's say, 20 ohm for R on times the 0.2 nanofarad, which is 4 nanosecond. So time constant of discharge is very small at 4 nanosecond. We can make the assumption that practically at 4 times 4 nanosecond, on the order of 16 nanosecond, cap is completely, this main cap is completely discharged back to 0. Now why are we saying is at 4 volt? Meaning that, why am I saying that the peak of this rise of the sawtooth for V2 gets to only 4 volt? That is effectively defined by this 4 volt, and the reason for that is proper design of this RC here, and this potentiometer is mainly for control purposes. That's why there is a potentiometer there. So meaning that we can adjust it in case it helps with better performance of the circuit, or better stability, or better shape of the sawtooth. Here is the RC for this series of 10K and 2 puff, or 2 picofarad. I'm going to write down here. So that's the RC for, let's say, if I define 10K as R2 and 2 puff as C2, then I have, let me push this to, I'm going to talk about it later. Okay, so I'm going to talk here about time constant R2C2, which is basically R2 times C2, which is 10 kilo ohm. Let's say the default value is for this potentiometer is max 10K times 2 picofarad, which is roughly 20 nanosecond. So you can see that the time constant of this RC is considerably more than the 4 nanosecond that we have for discharge time. It just indicates that when we have 4 volt appearing here at the output of the op-amp number 2, then the time it takes for the R2C2 to reflect reduction of 4 volt back to 0, or whatever it needs to be, is slower considerably compared to the time that the discharge happened, which is exactly what we desire, so that the circuit would not just start oscillating around the peak. With that said, with this proper design, quickly in this process, and during this time, which is, again, I am exaggerating it, the V2 at the output of op-amp 2 gets back to 0, and then the whole thing keeps repeating again. So after it gets back to 0, this whole thing keeps repeating itself. So like this. Okay, so now the whole idea, the remaining portion is I need to compute this time. What is it? Because I already computed this time, which is practically very small. So this time, if I refer to it, I can say it's effectively 4 times tau that I computed here. So this time effectively is about say 16 nanosecond. Alright, so let's compute this time here, which now requires me to go back to what I was doing at the earlier in terms of the, so let me change the color here and let me write it here. Okay, there you go. Okay, so what do we get from this guy? Well, this is during the charging up the main cap in the circuit and the V2 effectively. When we are doing that, the current I going through the cap is constant. That is the collector current for BJT, that is in the range of 40 to 0.4 milliamp. So I can say I, an integral from 0 to t dt is just the time. So I'm going to just write I times time. So the current of collector times time, the duration, is equal to C, and the voltage is going from 0 to 4 volt for the cap at the V2. So I can just say the current of collector times T divided by C, where C is 0.2 nanofarad. So I'm going to write 0.2 nanofarad is equal to 4. Okay, so let's consider the case that we have the maximum current, or let's say the case that we have minimum current, 0.4 milliamp. So this translates to, let's say, minimum current and maximum, let's say, current. So in the minimum current, we are saying 0.4 milliamp divided by 0.2 nanofarad times T, which is because minimum current is flowing through the cap, it takes maximum time. So T max we can afford in this circuit equal to 4. This is 4 volt. Alright, so we can just compute this time obviously. So it become 4 over 2, and there is a nano. So and then as a result it become just, let me make sure I'm not missing something. Okay, so we have 0.2 nanofarad that we just considered in the circuit, and we have 0.4 milliamp equal to 4 volt, and as a result we get 4 over 2, and there's a nanofarad there, and there's milliamp. So as a result we get milli over nano, so become micro. So if effectively this translates to T max equal to 2 microsecond. If IC is max, which means we are talking about, so we are feeding these range for IC. Now we are talking about 40 milliamp. So obviously we have 40 milliamp divided by 0.2 nanofarad, and then we get T min equal to 4 volt. So this obviously translates to T min equal to 20 nanosecond. So in summary, with the circuit that is designed here, what we managed to show is this T has a range of 20 nanosecond to 2 microsecond with the choice of designs. I mean, in terms of parameter values or component values in this circuit. Of course, we change the component, we can change this time frame. You can see for the 2 microsecond, which is the maximum range, effectively we can assume that since 16 nanosecond is much less than 2 microsecond, effectively the look of the waveform is very similar to a practically to a sawtooth. But when we get to the extreme range of minimum value for t 20 nanosecond, then that is comparable to the 16 nanosecond time that we have. So effectively, what I'm saying is, instead of sawtooth in that case, we are effectively getting into a triangular waveform, because it's more of a this look, with the drop or downside matching roughly the upside. So it become more of a triangular roughly. Alright, so we need to be careful about that, but basically we know the big picture. We can adjust components in the circuit so that we improve at whatever range of t, we improve the look of the waveform. I hope that this extensive and comprehensive analysis of operation of this circuit, which is, as I said, a sawtooth oscillator or generator circuit, is helpful in terms of showcasing how analog circuit that is formed and implemented using 3 operational amplifiers, 1 JFET N-channel and 1 BJT, is implementing a sawtooth waveform generator. I hope this is helpful.